Okay, the book gives us actual ways to do compass and straight edge constructions of these things. If you have tools that also allow you to do measurements, of course you can be fancier with this, but it is actually possible to do compass and unmarked straight edge constructions of inversion. Here are the instructions, which are written in your textbook. I also have them built in GeoGebra, so let's take a look at that. Of course, there's a separate one depending on whether the point's inside or outside of the circle. If you use tools that allow you to measure, you can get around that and have a single tool that does it. So this construction's kind of big. I'm going to have to move some things around a little bit to get it all to fit on the screen as we go along. But anyway, let's look first. Here's the construction when P is inside the circle to find P prime, and then a proof that that actually works. So the first thing you would do is take your straight edge and construct ray OP. So assume we don't know where P prime is yet. That's what we're trying to construct. But we have the circle centered at O, and we have our point P that's inside the circle. We can take our straight edge and extend a ray through OP. Next, we know how to create perpendicular lines, so it took some work with a compass and straight edge, but we do know there's a way to create a line through P perpendicular to ray OP. Okay. That gives us two intersections with the circle. We can take either one of those, so let's say Q is this intersection with the circle. We could then mark off the radius of the circle, OQ, and we could create at that point a tangent by going perpendicular to this radius. And we can see that actually went through P prime. The intersection of that tangent and the ray gave us P prime. Now to prove that that actually gives us what we want, here are some labels, and I'm going to have a hard time getting all this to fit. Let me move a few things down here. So if we look at our picture here, we need to show that x, which is OP, times x plus a, which is OP prime, we need to show that that is equal to the radius of the circle squared, which would be z in this picture, O to Q. So we need to show that z squared equals x times x plus a squared, or if we distribute x squared plus xa. Okay. It's just a matter of using the Pythagorean theorem on the appropriate triangles and following everything through here. So by the Pythagorean theorem, if we look at this triangle created with Q and P and O, so if we call this side y, this side x, and this side z, then we know x squared plus y squared equals z squared. Okay? So remember, we need to show that z squared equals x squared plus xa. So if we combine these two equations, we really only need to show that y squared, which would be z squared minus x squared, is equal to xa. Okay? If y squared equals xa, then x squared plus xa is going to equal z squared. Okay, then we have to look at a couple of other triangles. We also have that a squared plus y squared equals b squared. Let's see, that's this triangle, a squared plus y squared equals b squared. So we could subtract and get that y squared equals b squared minus a squared. In the bigger triangle, this triangle, z and b are the legs and x plus a is the longer side. So z squared plus b squared equals our hypotenuse squared, x plus a squared. We can FOIL that out and subtract z squared from both sides to get b squared equals x squared plus 2xa plus a squared minus the z squared. Then it's just a matter of substitution. So let's see if I can remember how I did this. Y squared is b squared minus a squared. Okay? So if we take that and plug this in for b squared, we get that minus a squared. Okay? A squared minus a squared is going to cancel out, so we've got a little bit simpler expression. We're left with y squared is x squared plus 2xa minus z squared. We can then substitute in that z squared is x squared plus y squared. And if we simplify that expression, this and that, and cancel like terms, we're left with y squared equals 2xa minus y squared. And then adding the y squared to both sides, we get 2y squared equals 2xa. Divide both sides by 2, y squared equals xa. So just a little bit of algebra and using the Pythagorean theorem on all three triangles and substituting in the appropriate ways, we wind up with y squared equals xa, which we knew was equivalent with this statement to showing that z squared equals x times x plus a. Okay, that the quantity we needed works out. That this side squared is equal to this times this. Okay, so the proof actually does work if we use the Pythagorean theorem and just chase through all of the measurements. Okay, if the point is outside the circle, the construction's a little bit different. We can find the point of tangency. Let's see. Take the note away for a second. That was something else. So we can start with OP. We can find the segment OP, and we can locate the midpoint of that segment, which could be inside, outside the circle, depends on where P is. Could be on the circle if P is exactly twice as far away there. Once we find the midpoint, we can create the circle centered at M going through O and P. And then QR connects the intersections of those two circles, our original circle and the circle centered at M. And then P prime turns out to actually be the intersection of those 2 points, of those 2 lines, the chord connecting Q to R in our original OP segment. Okay, I just say on the note here, you have several right triangles and the proof is very similar. I'm not going to chase through it here like I did on the previous one, but using the Pythagorean theorem, we can actually show that OQ times OQ, the radius squared, is equal to OP prime times OP. So that's the construction if it's outside. So theoretically, there are ways to use compass and straight edge constructions to find this. And that's one way to use GeoGebra to actually create a tool that does inversion. It's a little bit better if you just use the measurements and create a single tool, then you don't have to have it change when the point goes inside or outside of the circle.